Welcome back. In the first 3 sections of this chapter, we've been looking at the area in between 2 functions and what happens when we rotate that area to create a solid figure. In this section, we're going to take a little bit of a step back. Instead of looking at the area between 2 functions, we're going to look at the arc length along a function and what happens when we rotate that and create a hollow figure, for which we'll find the surface area instead of the volume. So we're going to go way back to something you're all familiar with, and that's the distance formula, or finding the arc length, if you will, of a straight line. So here's a picture of a straight line, and I've marked 2 points here, x1, y1, and x2, y2. And we all know the equation. Slope is equal to y2 minus y1 over x2 minus x1. And you might also recall that slope is another name for the first derivative. So if this is a function of x, this is f prime of x. Okay, and that applies to any linear function. Okay, at the top of page 475, you have some more equations, which guess what? You need to go in your equation booklet. And they give you the equations for finding the arc length of a function with respect to x and also a function of y. So make sure you get both of those into your notes. So let's look at this first example again. We know that for any linear function, f of x is equal to mx plus b. And then, of course, this is our first derivative. And so we're going to write this integral s between x1 and x2 is going to be the square root of 1 plus f prime of x squared dx. So that's the equation we're going to use. And now we're going to replace that f prime of x with this expression that we had. And I have s is equal to the integral from x1 to x2, square root of 1 plus y2 minus y1 over x2 minus x1, all of that squared dx. Okay, now we're going to rewrite the 1 so we can have a common denominator. When I take this expression and integrate it, this is what I get. x2 minus x1 squared plus y2 minus y1 squared divided by x2 minus x1 squared. And this is all inside that square root. And then on the outside, we have x, and we're going to evaluate this one from x1 to x2. Continuing on, this is going to be x2 minus x1 squared plus y2 minus y1 squared divided by x2 minus x1 squared, and then outside of the square root we're going to have x2 minus x1. Okay, one more step of simplification. We get the square root of x2 minus x1 squared plus y2 minus y1 squared, which you all should recognize as the distance formula. We're going to take what we just did with the linear function now and extend it to a function that's not linear to find an arc length. Okay, so this is a nonlinear function. Its equation is y equals x cubed over 6 plus 1 over 2x. And we are asked to find the length of the arc in between this point at x equals 1/2 and x equals 2. So let's write down what we know. Here's our function. And our limits are going to be from 1/2 to 2. Okay, notice this is not an ordered pair. This is just our limits of integration. Before we can integrate, we need to find the first derivative of that. So let's do that now. Y prime would be 3x squared over 6 and then we're going to have 1 over 2x squared. Okay, I'm going to factor out. Well, first I'll reduce this to 1/2, and then I'll factor out the 1/2. So I have 1/2 times x squared minus, not plus, one over x squared. So this is the expression that I'll be using in my equation. So now I have s equals the integral, and my limits are 1/2 to 2. And I've got square root 1 plus dy dx squared. So we'll just use this. That needs to be squared dx. Okay, after we multiply this out, we can factor out a 1/4. Then we have left x to the 4th plus 2 plus 1 over x to the 4th dx. Oh, and this is all square root. Okay, we know that square root of 1/4 is 1/2. And since that's a constant, we're going to go ahead and take that out. And now we can integrate. So we'll have 1. It should have been 1/2. So 1/2. I've got x cubed over 3 minus 1 over x. And we're evaluating from 1/2 to 2, which gives me 1/2 times 13 over 6 plus 47 over 24. And simplified, that is 33 over 16. So this is my answer. Okay, our next problem is a little different because we have both x and y raised to a power. So it looks just a little different from what we just did, but we're going to be doing the same thing, finding the arc length. For this problem, y minus 1 to the 3rd power is equal to x squared. We've got the graph of it here, and we were asked to integrate or find the arc length between 0 and 8. Okay, so the first thing we're going to do is solve for y, which is going to give us y is equal to x to the 2/3 plus 1. So then dy dx is going to be 2 divided by 3x to the 1/3. Okay, now we do have a little problem here because we were asked to go from 0 to 8, but what happens when x is 0? Since x is in the denominator here, the derivative's not defined there. Okay. Since dy dx is not defined for the entire length that we need, we're going to have to now solve for x and have dx dy. So let's get rid of this. So when I solve for x, this is what I get. Okay, and if I choose positive values, then I can get dx dy equal to 3/2 of y minus 1 to the 1/2. So this interval from 0 to 8 on x corresponds to an interval from 1 to 5 on y. So this is what my equation is going to look like. You notice I just took this expression for dx dy, moved it into the square root, and then squared it. Okay, simplifying. I'm going to get integral from 1 to 5 9/4 y minus 5/4 dy. Okay, I can take a 1/4 out of both of those when the square root of, if I have a 1/4, the square root of that was 1/2. So now I've got 1/2. That's the integral from 1 to 5 square root of 9y minus 5 dy. Okay, now I'm ready to integrate. I get 1/18 times 9y minus 5 to the 3/2 power over 3/2 from 1 to 5. This is going to give me 1/27 times 40 to the 3/2 minus 4 to the 3/2. And this is approximately equal to 9.073. In this example, we're going to use the same formula, but this time we're looking at a function that's defined in terms of natural logarithm and cosine. So this is my function equation, y equals natural log of cosine of x. And I'm asked to find this arc length, just this heavy marked part from 0 to pi/4. Okay, for this function, y prime first derivative is negative sine x over cosine x, which would be, of course, negative tangent x. So using our equation, we're going to have an integral from 0 to pi over 4 square root of 1 plus tangent squared x dx. Okay, then we'll use our trig identities and rewrite 1 plus tangent squared x as secant squared x. And of course, the square root of secant squared is just going to be secant x dx. So when I integrate, I will have natural log of the absolute value of secant x plus tangent x evaluated from 0 to pi over 4. And this gives us natural log of the square root of 2 plus 1 minus natural log of 1, which is approximately equal to 0.881. As you're working your homework assignments, please make sure that you're paying particular attention to the form that's requested for your answer. They may ask for 2 decimal places, they may ask for 3 decimal places. Just follow the instructions. Okay, I'm going to skip over the next example. It has to do with hyperbolic trig functions, which I'm not going to tackle in this class. So we'll skip over example 5 and go straight to examples 6 and 7. Earlier in this chapter, we took a plane area that we'd found the area for and rotated around a axis to create a solid of revolution. Now we're going to do the same thing with an arc length. We're going to rotate it around an axis of revolution, and instead of creating a solid, we're just going to create like a hollow shell and find the surface area of that shell. So let's take a look at how that goes. In this problem, I've got this function f of x equals x cubed. And I'm going to rotate it around the x-axis. And it's going to give me a shape kind of like the bell of a horn. And I want to find then the surface area of that. Okay, you do have some equations for this. Those are found on page 479. And those will be very helpful to you as you work through these problems. Okay, we're asked to find the surface area when we take this curve from 0 to 1 and rotate it around the x-axis. So here's our function, and this is our equation. S is equal to the 2 pi times the integral. Let's put the 2 pi in there. Just like we do the sides of a cylinder, our equation basically is 2 pi r, but we have to integrate since the surface is not nice and flat like it is in a cylinder. So we're going from 0 to 1. And we use x cubed, which is our r of x, times the square root of 1 plus the derivative f prime of x, which in this case is 3x squared, and we square that, dx. Okay, when I square this, I'm going to get 9x to the 4th. And so for my dx, I'm going to need 36x cubed. To do that, I'm going to take out a factor of 1 over 36. Let's just put the 2 pi over that. And now I can have inside the integral the 36x cubed. And this is 1 plus 9x to the 4th to the 1/2, that's our square root, dx. Okay, reduce this to pi over 18. And now when I integrate, I get 1 plus 9x to the 4th, and all of that to the 3/2 power, divided by 3/2, evaluated from 0 to 1. Okay, I can take this 3/2 out with the pi over 18, which will give us pi over 27. And when I take this and evaluate at 1, I'll get 10 to the 3/2. Minus the value at 0. Well, if this is 0, I have 1 to the 3/2, which is just 1. So 10 to the 3/2 minus 1. And this works out to approximately, not exactly, approximately 3.563. Okay, here's another function that we're going to rotate this time around the y-axis and create a surface of revolution. This one looks kind of like a cup. Okay, and we're going from 0 up to 2 on the y-axis, and from 0 over to the square root of 2 on the x-axis. Okay, for this curve, our function is f of x is equal to x squared. F prime of x then would be 2x. And we're going to go from 0 to square root of 2. Those would be my limits of integration. So start off with our basic equation, x equals 2 pi times the integral from 0 to square root of 2 x times the square root of 1 plus 2x squared dx. On the inside, I'm going to need a factor of 8. So I'm going to bring an 1/8 out to the outside. 2 pi over 8, integral from 0 to square root of 2. And now on the inside, I have 1 plus 4x squared to the 1/2 times 8x dx. So now this reduces to pi over 4. And integrating here, I have 1 plus 4x squared to the 3/2 power over 3 over 2. Evaluated from 0 to square root of 2. I'm now going to take out this denominator, which becomes then 2/3. So I have now pi over 6 times 1 plus 8 to the 3/2 minus 1, which would be the value at 0. And my final result is 13 pi over 3. And if I change that to a decimal, I get 13.614. So that is integrating to find the area of a surface of revolution when I rotate the arc of a function. Okay, this concludes our lessons for 7.4. And once again on the homework, just be sure that you check the specifications for the answer, how many decimal places you need to have.